Welcome back to the deep dive. Imagine for a moment typing just a few words, a simple phrase, and watching a truly stunning, lifelike image just materialize before your eyes. It feels a little like magic, right?
It really does.
But how did we actually get here from, basic computer graphics to these incredibly sophisticated creative machines?
Well, it's a really fascinating journey, decades of innovation, actually, and that's precisely our mission today, to kind of pull back the curtain on AI image generation.
Exactly. So this deep dive is all about tracing that incredible evolution, highlighting the breakthroughs that really defined each era, and then we'll zoom right in on Google's latest Gemini 2.5 flash image.
Right. Our goal is really to help you understand not just what these models are doing, but how they've advanced, what makes this new Gemini model unique, and importantly, where this whole field seems to be headed.
Yeah, what's next? So whether you're just really curious about the tech itself, or maybe you're grappling with these new creative tools in your work, or perhaps you just want to stay ahead of the curve, this deep dive should give you the essential knowledge you need to feel truly well-informed.
Let's get into it.
Okay, let's unpack this, starting maybe with the very first attempts at machine creativity. Because the idea of machines creating art isn't actually that new.
Not at all. We're talking centuries back, really. Things like Mayer-Det's automaton in the 1800s, it could draw pictures.
Wow.
And then much later, Harold Cohen's Aaron program in 1973, Aaron could generate original art, but it was all based on rules that Cohen programmed in, didn't learn anything.
Right, it wasn't learning patterns. So what was the real turning point, the aha moment that led to what we have now?
That big shift that really came with the deep learning revolution, say early 2010s, the success of convolutional neural networks, CNNs like AlexNet back in 2012, that showed us something really profound.
Which was?
That machines could learn complex visual patterns directly from data. This ability to recognize things, to understand what a cat or a tree actually looks like in pixels, that became the essential foundation for generation.
Okay, so first they had to learn to see before they could learn to imagine. Makes sense.
Exactly. Once a machine could accurately see, well, then you could start teaching it to generate.
And from that initial spark, we jump pretty quickly into what some people call the adversarial era. Let's talk about generative adversarial networks, GANs, from around 2014. I always think of them as a sort of high-stakes game of cat and mouse, or maybe forger and detective.
That's a perfect analogy, actually. You've got two neural networks. There's the generator, the forger, trying its best to create fake images that look totally real.
Right.
And then there's the discriminator, the detective, whose only job is to look at an image and decide, is this real or is it a fake from the generator?
And they train together, constantly trying to outsmart each other.
Precisely. They're locked in this zero-sum game. The generator gets better at fooling the discriminator.
And the discriminator gets better at spotting the fakes.
Exactly right. And this adversarial dynamic, it was a real game changer. It forced the generator to learn the subtle details, the textures, the lighting of real images in a way no simple rule-based system ever could. That really opened the door to the first truly photorealistic AI images.
Okay, so that was a major leap. But I remember hearing GANs weren't perfect. They had problems.
Oh, definitely. Training GANs was, well, notoriously unstable. It could be really difficult to get them to converge properly. And they often suffered from something called mode collapse.
Mode collapse? What's that?
It means the generator gets stuck producing only a very limited variety of outputs. Like, it might learn to draw one specific type of dog really well, but fail to generate any other breeds, even if they were in the training data. It missed the diversity.
I see. So if GANs were tricky and sometimes limited, what came next? Did researchers find another angle?
They did. They explored a more probabilistic approach with variational autoencoders, or VAEs, which actually came out slightly earlier, around 2013.
VAEs, how do they work? Is it still a game between two networks?
No, it's a different philosophy. Think of VAEs more like an elegant compression and decompression system. You have an encoder network that takes an image and compresses it down into a much smaller representation, like its essential features. We call this the latent space.
Kind of like the core idea of the image.
Sort of, yeah, the essence. And then a decoder network takes that compressed essence from the latent space and tries to reconstruct the original image as accurately as possible.
Okay, encoding and decoding. What was the key innovation there compared to just, say, compressing a file?
The really clever part is that the encoder doesn't just map the image to a single point in that latent space. Instead, it maps it to a probability distribution like a fuzzy region.
Okay. Why is that important?
That probabilistic mapping allows for much smoother transitions between generated images and, crucially, much more stable training compared to GANs.
So more stable, but was there a downside?
Yeah, the trade-off was often image quality. VAEs typically produced images that were a bit blurrier, maybe less sharp and detailed, compared to the best GANs at the time. Stability came at the cost of some visual crispness.
Right, so GANs gave us realism but were unstable. VAEs were stable but maybe a bit blurry. It feels like we needed something that combined the best of both worlds.
And that's exactly what happened next with what many consider the true paradigm shift, the denoising revolution powered by diffusion models. The key paper, DDPM, came out in 2020. This tech is really the engine behind most of today's top models.
Diffusion models. Okay, I've heard they're inspired by thermodynamics, like physics.
That's right, believe it or not. The core idea is about creating order from chaos. It works through this really elegant two-part process. First, you have the forward process.
Okay.
This involved taking a perfectly clear image and deliberately messing it up. You gradually add tiny amounts of noise, step by step, over maybe thousands of steps, until the original image is completely lost in pure static, like an old TV screen with no signal.
Okay, so you destroy the image systematically. Why?
Because the real magic is learning to reverse that destruction. That's the reverse process. An AI model, often a type called a UNet, is trained to do the exact opposite.
Undestroy it.
Precisely. It starts with pure random noise that's static, and then iteratively predicts and subtracts the noise, step by tiny step, effectively reversing the diffusion process until a coherent, clean image emerges.
Wow, okay, that does sound almost poetic, like sculpting an image out of noise.
It's a very powerful concept, and it brilliantly solved the main problems with JAX, the instability, the mode collapse. Diffusion models could achieve incredibly high fidelity and fantastic diversity in their outputs.
So that sounds like the breakthrough everyone was waiting for. But nothing's ever perfect, right? Was there a new challenge with diffusion models?
There was. The iterative nature, all those tiny steps of denoising, made the generation process quite slow and computationally expensive, especially early on.
Right, so we have this amazing new engine, but it needs refinement, maybe some turbocharging. Which brings us to the modern toolkit, how today's models are actually built to be faster, smarter, and more capable.
Exactly. And one huge architectural shift that helped was moving beyond just those convolutional networks we mentioned earlier. The transformer architecture, which first revolutionized language processing in 2017, turned out to be incredibly powerful for images too.
Transformers. I know they use something called self-attention. How does that help an AI understand an image better than, say, a CNN?
Well, think about how you look at a complex scene. You don't just see isolated pixels or small patches. Your brain instantly connects different parts. The person in the foreground relates to the building in the background. The lighting affects everything.
Okay.
Self-attention allows the model to do something similar. When processing any part of an image, like a small patch, it can weigh the importance of all other parts of the image simultaneously. It grasps the global context, the relationships between elements, much more effectively than CNNs, which tend to focus more locally.
Ah, I see. So it gets the big picture understanding, not just the details in isolation.
Precisely. Vision transformers, or VITs, basically chop the image into patches, treat them like words in a sentence, and let the transformer analyze the whole sequence. Game-changing for visual understanding.
But these models with transformers and diffusion, they got enormous, right? Billions, even trillions of parameters. How do you run something that huge efficiently?
That's where another crucial innovation comes in. Mixture of experts, or MOE. It's a clever way to manage massive model size without incurring massive computational costs for every single prediction.
Mixture of experts. Sounds intriguing. How does it work?
Instead of having one gigantic network where every single parameter is used for every task, a MOE model has many smaller, specialized expert networks inside it.
Okay.
And there's a gating network that acts like a traffic controller. When an input comes in, the gating network quickly decides which few experts are best suited for that specific input and routes the data only to them.
So most of the model stays inactive.
Exactly. The model can have a truly enormous total number of parameters, giving it huge capacity and knowledge, but for any given input, you only activate and compute a small fraction of them. This makes inference much faster and cheaper. It's absolutely critical for enabling models like Google's Gemini family to operate at scale.
That's really smart. Okay, so we have powerful architectures like transformers, efficient scaling with MOE, but how do we get the text part? How do these models understand our prompts so well?
That leads us to perhaps the single most important catalyst for the text-to-image revolution we see today: CLAP, which stands for Contrastive Language Image Pre-training, developed by OpenAI in 2021.
CLIP, I've heard this mentioned a lot. It's like the Rosetta Stone for images and text.
That's a great way to put it. Before CLIP, guiding image generators with text prompts was, frankly, quite clunky. You could use simple captions, but the AI didn't really grasp the deep semantic connection between the words and the visual concepts.
So how did CLIP crack that code? How did it build that bridge?
CLIP used a clever approach. It trained two separate encoders simultaneously, one for processing images and one for processing text. Crucially, it trained them on a massive dataset, 400 million pairs of images, and their corresponding text descriptions scraped from the internet.
400 million. Okay. And what did it learn from all that data?
It learned to project the outputs of both the image encoder and the text encoder into a shared embedding space. Think of it like a common meeting ground where the meaning of an image and the meaning of text can be directly compared.
So similar concepts end up close together in this space, regardless of whether they came from a picture or words.
Exactly. It used contrastive learning. The model was trained to maximize the similarity score for correct image-text pairs, like a picture of a dog and the text photo of a dog, and minimize the similarity for incorrect pairs, like the same dog picture and the text photo of a cat.
I see. It learns to associate the right words with the right visuals very strongly.
Precisely. And this ability to deeply understand the semantic relationship between any text and any visual content provided the essential steering wheel for diffusion models. CLAP allows the text prompt to effectively guide the denoising process, telling the model what kind of image to sculpt out of the noise. That's what unlocked the really powerful, nuanced text-to-image generation we have now.
Okay, that makes so much sense. CLIP was the missing link.
Yeah.
And that brings us right up to the present day, and specifically to Google's Gemini 2.5/image. Given all this history, this amazing toolkit diffusion, transformers, MoE, CLIP, what makes Gemini 2.5/image stand out? What's the unique contribution?
Well, the core differentiator for the entire Gemini 2.5 family, including the Flash image model, is its natively multimodal architecture. This is really key.
Natively multimodal. What does that mean in practice compared to other models?
It means that unlike many earlier approaches that might sort of bolt together separate pre-trained models for text and images, Gemini 2.5 models were designed and trained from the ground up to understand and process multiple types of beta text, images, even audio within a single unified architecture.
Ah, okay. So it's not like having a separate brain for words and a separate brain for pictures that then talk to each other. It's one integrated brain that understands concepts across different senses, so to speak.
That's a very good analogy. It develops a single intertwined internal representation. For example, the concept of an apple isn't just linked text features and linked visual features. It's a single unified concept within the model that has both text and visual aspects inherently part of it.
And this unified understanding, built on that sparse MoE transformer architecture you mentioned, that's what enables its more advanced capabilities.
Exactly. It allows for much more sophisticated reasoning across modalities. It's not just generating an image from text, it's understanding the interplay between them much more deeply. This foundation unlocks features that go way beyond basic text to image.
Okay, this sounds genuinely different. What are some of those key capabilities that really show off this native multimodality?
One of the most impressive is its conversational multi-turn editing. This is a big one. You can upload an image, maybe a picture of a blue sedan.
Right.
Then you can just say, using natural language, turn this car into a convertible. The model does it. Then you can follow up with, okay, now change the color to bright yellow. It remembers the context that you're still talking about the same car, now a convertible, and applies the new change.
Wow. So you don't have to re-upload the edited image each time or restate the whole prompt. It maintains the state of the conversation.
Exactly. It enables this fluid, iterative refinement process that feels much more like collaborating with the designer than just giving one-off commands. That's a huge deal for creative workflows.
I can see that being incredibly useful.
Yeah.
What else stands out?
Another key feature is stateful character and style consistency. This tackles a common frustration with AI image tools. You create a character you like, but then trying to put that same character in a different scene results in them looking slightly different character drift.
Yeah, that's really annoying.
Gemini 2.5 is designed to better preserve a character's identity across multiple images and scenes. It can also maintain a consistent artistic style more reliably. Then there's multi-image fusion.
Fusion. like combining images.
Right. You could take an object from one image, maybe a specific statue, and a background scene from another image, like a park, and use a text prompt like, put the statue in the park near the fountain.
Hmm.
The model needs to understand the spatial relationships, lighting, and semantics to blend them convincingly.
That requires some serious reasoning.
Mm.
And I also heard it leverages Google's broader knowledge base.
Yes, being part of the larger Gemini family means it acts as a reasoning engine, too. It can understand and even edit things like a hand-drawn diagram of the solar system based on factual instructions, or help visualize a complex physics problem. It integrates world knowledge.
And what about text? Lots of models struggle with putting clear text in images.
That's another area where Gemini 2.5 Flash Image is notably strong. It excels at rendering clear, well-placed text, which is great for things like creating logos, posters, or annotating diagrams accurately, a historical weakness for many models.
Okay, so it sounds powerful and versatile. How do people actually use it? And what about practicalities like cost and safety?
It's pretty accessible. Developers can use it via the Gemini API, Google AI Studio, or Vertex AI for more enterprise applications. There are also integrations happening with tools like Adobe Firefly, Adobe Express, Figma, and even Poe, the chatbot platform.
And the Flash part of the name, does that mean it's fast and efficient?
That's exactly the idea. Flash indicates it's optimized for low latency and efficiency, making it suitable for interactive applications. Cost-wise, it's quite competitive, around 0.039 cents per standard image generation, which is based on output tokens.
And safety. You mentioned Synthety.
Yes, critically important. All images generated by Gemini 2.5 Flash Image are embedded with Synthety. This is an invisible, permanent digital watermark developed by Google DeepMind. It allows the image to be identified as AI-generated even if it's later edited or screenshotted, which promotes transparency.
That's good to hear. So putting it all together, Gemini 2.5 Flash Image seems less like just another image generator and more like a foundational piece for these more interactive, conversational, and context-aware creative systems.
That's precisely how Google seems to be positioning it. It's about the workflow, the interaction, the reasoning, enabled by that native multimodal core.
Okay, but it's not alone out there. The competition is fierce. How does Gemini 2.5 Flash Image stack up against the other big names like DALL-E 3, Midjourney, and Stable Diffusion 3?
Right, let's quickly survey that landscape. First up, OpenAI's DALL-E 3. Its most defining characteristic is probably its tight integration with ChatGPT.
Yeah, ChatGPT basically acts as a smart prompt engineer for you, right?
Exactly. You can give ChatGPT a simple idea, and it expands it into a detailed, effective prompt for DALL-E 3. This makes it incredibly user-friendly and really strong on-prompt adherence, doing exactly what you asked for.
So, great for accessibility and getting literal results? What's the potential downside?
Well, because it's so literal and relies on ChatGPT's interpretation, it can sometimes feel a bit less creatively surprising, maybe less artistic than some others. And the editing process isn't as conversational or integrated as what Gemini aims for.
Okay. Then there's Midjourney, the
Yeah.
artist's favorite, perhaps.
Often, yes. Midjourney is proprietary, closed source, and famous for its very distinct, often quite beautiful, opinionated aesthetic. It excels at producing cinematic, artistic, visually stunning images right out of the box.
Unmatched artistic quality seems to be its calling card. It has powerful editing tools too, though not conversational ones, right? Like varying regions, panning, zooming.
Correct. Very powerful non-conversational editing. The main challenges with Midjourney can be the steeper learning curve. It uses a specific syntax in Discord, and sometimes its strong artistic style can override your specific instructions if you're aiming for something more mundane or precise. Plus, images are public by default in the lower tiers.
Got it. And finally, the open source champion, Stability AI's Stable Diffusion 3.
Right. Stable Diffusion's biggest advantage has always been its open source nature, offering maximum control, customization, and fine-tuned possibilities for those with the technical skills.
And the new version, SD3, has a new architecture.
Yes, it uses something called a multimodal diffusion transformer, MMDIT. A key feature is that it uses 3 different text encoders, 2 types of CLIP models, plus another called T5, to achieve a really deep understanding of the text prompt.
3 text encoders. Why so many?
The idea is that different encoders capture different nuances of language, and combining them gives the model a richer, more robust understanding of the prompt's meaning and structure. This helps it excel, particularly in typography. SD3 is currently seen as the leader in generating clear, accurate text within images.
That's a big deal. But the trade-off with open source is often usability and hardware requirements, isn't it?
Definitely. To run SD3 effectively locally, you generally need significant technical know-how and a powerful GPU, often with 24 GB of VRAM or more. The user experience also depends heavily on which third-party interface you choose to use.
Okay, so if we try to compare them head-to-head really quickly, prompt
Yeah.
following.
Gemini 2.5 Flash image benchmarks, well, often leading in user preference tests like the El Marina chatbot benchmark, which includes image generation. SD3 is also excellent. DALL-E 3 is very literal. Midjourney can be more interpretive, but produces hyper-real results.
Editing and consistency.
This seems to be a key strength for Gemini with its conversational, stateful approach. The others have capable editing, but it's less interactive.
Speed and costs.
Gemini Flash is explicitly designed for low latency and cost effectiveness. Others vary, and local SD depends heavily on your hardware.
And text generation.
SD3 currently holds the crown due to its multi-encoder setup, but Gemini 2.5 Flash image is also reported to be very strong, likely benefiting from its unified training.
So, to wrap up the comparison, who is each model really best suited for, if you had to give a quick recommendation?
Okay, rough personas. Gemini 2.5 Flash image seems ideal for those needing interactive conversational workflows, iterative refinement, context awareness, and strong multimodal reasoning. Think designers, developers building integrated apps, educators.
Makes sense.
DALL-E 3 is great for general users, content creators, anyone who values ease of use via ChatGPT and wants reliable, literal results from their prompts.
Okay.
Midjourney remains the top choice for artists, illustrators, and designers, prioritizing unique, high-impact artistic quality and aesthetics above all else. And Stable Diffusion 3 is for the researchers, developers, AI enthusiasts, and power users who demand maximum control, customization, fine-tuning capabilities, and leading-edge typography, provided they have the technical skills and hardware.
That's a helpful breakdown. So, looking beyond these current giants, where is this whole field of visual synthesis headed? What's on the horizon?
Well, the really exciting frontiers now seem to be pushing beyond static, flat images into dimensions like time and depth.
You mean things like text-to-video generation and creating 3D models from text?
Exactly. Generating video is exponentially harder than images because you need temporal consistency. Objects, characters, lighting, everything needs to stay coherent and behave plausibly frame after frame.
Yeah, that sounds incredibly complex.
It is. Models like OpenAI's Sora, Google's own Veo, Meta's Movie Gen, they're essentially trying to build rudimentary world simulators. They operate on what some researchers call space-time latent patches, trying to model not just space but also how things change over time. If this technology matures, it could completely democratize video production and animation.
Imagine typing a script and getting a short film back. Mind-blowing. And 3D.
3D model synthesis is another huge area. Automating the creation of 3D assets, characters, objects, environments would be transformative for industries like gaming, virtual and augmented reality, architecture, industrial design, you name it.
How are they approaching that? Is it like diffusion for 3D?
Several approaches are being explored. Some use 2D image generators, like the ones we've discussed, to create multiple views of an object, which are then reconstructed into a 3D model using techniques like neural radiance fields, or NeurFs. Others are working on generating 3D meshes directly. Companies like NVIDIA, Meta, and startups like Meshi are pushing hard here. It's a massive potential market.
So simulating worlds in video in 3D, what other research frontiers are emerging?
Beyond new dimensions, there's intense focus on improving control, speed, and ultimately agency.
Control and speed seem obvious goals. Real-time generation.
That's the dream, isn't it? Getting instant visual feedback as you type or modify a prompt. Techniques like rectified flows, which SD3 uses, and progressive distillation are helping models generate images much faster, moving towards that real-time goal.
And better control. Going beyond just looking plausible.
Right. Moving towards images that are not just visually convincing, but also factually correct or precisely controllable. This involves deep research into things like disentangled representation learning, being able to change one specific attribute, like an object's color, without affecting anything else. And also causal reasoning, making the AI understand cause and effect within the generated scene.
And you mentioned agency. What does that mean in this context?
This is where things get really interesting. It's the idea of these generative models becoming components like the eyes and hands within larger, more autonomous AI agents.
So an AI agent could decide on its own to generate an image.
Exactly. Imagine an AI assistant tasked with writing a report. It might decide it needs a specific diagram, use an image generator like Gemini to create it, maybe iterate on it based on its understanding of the report's goal, and then insert it all without explicit human prompting for each step.
Wow. That shifts the AI from being just a tool we command to being more of a collaborative partner.
Precisely. A partner that can perceive, reason, and act using generation as one of its capabilities. This could fundamentally change how we approach complex tasks involving creativity and problem solving.
Okay, let's try to bring this all together. We've traced this incredible journey, haven't we? From early rule-based art programs to GANs and VAEs, the diffusion revolution, and now these incredibly sophisticated multimodal models like Gemini 2.5 Flash Image.
Yeah, and Gemini, with its native multimodality, its conversational abilities, its focus on reasoning and efficiency, really does feel like it's positioned as a foundational piece for this next era of more interactive and integrated AI creativity.
And looking forward, it's not just about getting prettier pictures anymore, is it?
Not at all. The horizon is about simulating dynamic worlds video, 3D with models that understand time, physics, causality, and offer us much finer control, potentially operating within these larger, more autonomous agentic systems.
So here's something for you, our listener, to really think about as we wrap up. Consider how these rapidly evolving capabilities, moving from generating just one static image to maybe having an AI agent plan, create, iterate, and visualize across multiple dimensions like video or 3D. How might that fundamentally change the way you approach creativity or solve problems, or maybe even just how you consume information in the very, very near future?
It's a profound shift, the line between what we can imagine and what we can instantly visualize and interact with in the digital realm. Well, it's about to get incredibly blurry and potentially incredibly powerful.
A lot to think about. Thanks for joining us on this deep dive.